Alright, thanks. I actually have some things with some 3D animations in stereo with 3D glasses, so anyone who wants them, and maybe switch to the browser at the end, which is behind, that has some of those. And thanks for, I want to thank Kristen.
Thank you, Bob.
Thank you.
And this is an algorithm for what's called a virtual trackball, and I'll talk about the virtual trackball that allows interactive 3D visualization and without a machine, without an actual device. It's called an actual trackball, and there have been a variety of implementations. So I'll start out with the actual hardware trackball. There's a page with all the trackballs of the past. Trackballs are things I discovered in that. Maybe the earliest one is in some of those video games in the arcades where there were balls to control which way you were going, so it had a direction and it could actually roll in real time. So that's the one down here. Marble Madness, 1984 on the far right. But there have been several trackballs, physical trackballs, hardware trackballs in the past. And so there's a page you can find by Sha Li, the mathematician in California. And they're even being used up to the present. There's trackballs past and present. NVIDIA has a new patent on their trackball. So what's nice is that you can actually have a trackball from all the way, not only just recently, but since these past trackballs back to the early 80s of video games and mouse trackballs, current trackballs in NVIDIA. I needed to rotate some things in 3D when I was working on gene discovery for cancer and to show the mechanism of cancer progression. It's something we share with Gary in the DNA session. And the people I was working with asked me if I could visualize that interactively, the mechanism of discovering out of several gene expressions out of 7,000 that there were actually 3 in the static picture that, not in any one dimension or 2 dimensions, but in 3 dimensions, the overexpression of one gene, the underexpression of another, and the phenomenon in the third separated the aggressive from the dormant. And so I needed to learn about trackballs because not everybody would be able to interact with the animation with a hardware trackball. So I looked at the trackballs, and some of the earliest trackball math, if you can see on the right, has a lot of transcendental functions and matrices, and it's pretty involved in finding axes and angles. So that was the original trackball patent by Chen in '88. It was patented actually. And the idea was an interactive 3D rotation using a 2D control device with a mouse. Basically, could you use your mouse to do a trackball? And we'll talk about how that works a little bit later. This is more about what you can do with it. And there have also been Quaternionic trackballs, but this one, and particularly in this Google Tech Talk, actually avoided the whole beauty of quaternions, of quaternion to matrix and stuff. I think I mentioned that. So here is what I was able to do at the time, and a lot of this is about the end of the Flash era of animation. This was all in Flash and ActionScript, which is no longer available, and some of the what this is about is how I could try to do some of the things in Flash, done in Java also. Now there are much better tools with Python, but at the time I was using Desmos. Could I actually do a 3D trackball in Desmos? Could I turn Desmos into a 3D animation? thing. And so here's what was done at the time with Flash, with interactive animation. And I was also interested in topology, and even this is really a quaternionic thing, 720 degrees. It actually says in here, 720 degrees of entanglement. This is in the book Gravitation by Misner, Thorne, and Wheeler. And they were very old school visualization and animation. They had 9 frames of a pencil drawing to show that if you took a ball in the center of a room, tied it with strings to the walls, and you could turn it, if you turn it once, there's no way to untangle the strings, but 2 times about a vertical axis, 720 degrees, 4 pi, 2 tau, you can untangle the strings without ever moving the ball. And that's a homotopy thing about the fundamental group of SO3. And so here was interested in animating that, and the thing about, to be able to use a virtual trackball, this doesn't have to just be a static animation from a particular view. When I go to the browser at the end, you can see with your mouse, you can actually look at this from any point, and you can roll it however many times over and over you want. What's that doing? That is actually visualizing the homotopy of from 2 full turns about the vertical axis to a constant. So there are lots of things you can do with interactive 3D animation at various levels. And here was conic sections for a pre-calculus class. And a lot of the demonstrations there rotate the plane, tilt the plane. But if you just leave the plane z equals 0, the algebra works out much more nicely. And then you can see what happens as you rotate a cone that's just, its vertex is shifted, and you see the hyperbolas and these are all using, and at the end maybe it'll be time to go with 3D glasses on the browser. I'll give you out the 3D glasses because I'll stop in a few minutes and we can turn off the lights, and you can see how a lot of these things, this is great for outreach. You can do torus knots with these kind of rotations, and the key here is the formulas to actually implement rotation is so simple that you can even do it in Desmos. Say 3D rotations in perspective. That's torus knots. Kids really love this, and then you can ask them, change the number of turns about one circle and about the other circle, and they go to 100 or 23 different primes, and you see all kinds of different things. But this is visualizing using point clouds, dotted tori, so that you can see through things and you can see the full thing. So I can show you some of that later. And recently I was using dotted tori to graph rational functions, and you can really see the correspondence between cross zeros, factors with even and odd powers, how they either bounce off or cross y equals 0, or infinity. It happens perfectly, and you use stereographic projection, great tool so it's really like taking your graph paper and taking the top and the bottom together, and the right end and the left end together, and getting that torus, and you have the entire plane. So really in this representation, 0 is the outer equator, infinity is the inner equator, and the circles on the right and left are 1 and -1, and the top circle and bottom circle. So I really like these. Here's Schumacher did a Quaternionic arc ball, but it was path independent. So, and it also doubled the angle of rotation. As you pulled your mouse by theta, it would rotate the thing to theta. That was considered a feature, not a bug, because with only a half-turn pull, you could rotate the object the full turn. That was, you could decide whether you like that as a feature or a bug. Here, you see, as you pull and it would show the arc in Quaternion space. And here's the Flash version of the transvection, the reflection-based algorithm I'm going to tell you about. That's simple enough to do in a couple slides. Yeah. So this is rotating platonic solids interactively to see them from any direction, and there were all those. That was in Flash, again, no longer available unless you saved your Flash player. Flash era, we had harmonic motion and epicycles. So harmonic motion can also generate an internal circle. And Flash era, again, it was really nice. This was in Journal of Online Math at the time, is generating the sine curve from the up and down motion versus how far the circles had rolled out. And now here, you can do it in the Desmos era. So that's what I've liked about the Desmos era, is being able to do some reconstruct stuff that was really pretty hard to program in Flash and ActionScript, using just write down the formulas and pull the points or slide the sliders, get the cosine, the right and left motion, or the up and down. Cosine is the right and left motion, so you have to visualize it vertically. And so what I wanted to do here, again, animating formulas that the derivations of things like sine and cosine addition formulas are typically pretty involved, but you can really, just from an animated diagram, you can derive them and complex multiplication simultaneously, just as a linear combination. Pythagoras pops out too. The differential equations for sine and cosine are all in this linear combination diagram. So it just takes things that are really opaque and makes them more transparent. It's fun. You can do things like algebra. Oops. Algebra things with there. You can do prime sieve visualizations with multiples of different numbers. You can do, here's a kind of a cute generalization of this, the familiar Zeno case of geometric series. You can find the initial fraction that always leads to making the sum 1, and it turns into a instant proof without induction of the geometric series formula. Binomial coefficients, people don't know that often think that you can't compute binomial coefficients up to n equals 1,000. You can do it very easily, even in Desmos, if you use logarithmic approaches. And so here is 3D rendering comparison. Here is, I think, that's static, old school version of 3D rendering. How do you find the point on your image plane? You just look at the line interpolation of your camera point, your viewpoint, and the data point. And you find the point where that intersects. But it's much easier if you can see it in an animation. Whoops. Up there. Here is mouse control rotation. There was one supposed to be there. There. Here's 3D rendering animated. Where does that vector go on the screen? We just find the point, the interpolation point or extrapolation point that hits the image plane, which is just the line, the plane through the origin perpendicular to that. So Desmos lets you animate and see what's happening when you're rendering a point in space onto the image plane. This was the old version. It's a lot more fun when it's moving in color. Here then is 3D. Here's 3D in Desmos. You can actually do 3D in Desmos. But I wouldn't want to do it with the matrices or the trigonometric humongous formulas find the axis. There's a simple trick that's the way that you can do 3D animations that turns out to be a representation of quaternions. So here's first how the mouse-controlled rotation works. You move the mouse, you're pulling the object in its glass ball. So there, I can animate that. As you move your mouse, you're specifying a unit vector. And 2 consecutive frames come from 2 consecutive unit vectors, and 2 unit vectors in R3 specify a unique rotation that takes the first to the second and preserves the plane. That's the key math. two unit vectors in R3 specify a unique element of SO3 that takes the first and the second. That's not enough, because you could always do a turn around the final or a pre-turn around the initial. That wouldn't be unique. But if you preserve the plane, it's unique. That's the math. And there's a simple way to do it by reflecting across the first vector and then reflecting across the midpoint, the bisector. But you can reflect across the bisector or the final, and that's what the next animation is here. This is using the clock to show. How do I rotate the clock in R3? This is a whole clock from 12 to 4. I flip around the noon axis and I flip around the 2 o'clock axis. That's the algorithm. But I could also flip around the 2 axis and the 4 axis, right? That's going to take 12 to 4. 12, flip across 12, flip across 2, flip across 12, leaves 12 alone. Flip across 2 takes 12 to 4. Flip across 2 leaves 2 alone. And takes 12 to 4, and flip across 4 afterwards leaves 4 alone. That's the whole math. And the idea is, it doesn't matter what those two are as long as they are 2 apart. If your reflections are 2 apart, then you will get the same rotation. And you can also reverse either vector. And you'll still get the same reflection. And that's a representation of the rotation group that's 2 to 1. If you think that equivalence classes that are, say, 30 degrees apart and 30 degrees plus 180. I'll go to degrees so I don't have to have the debate between pi and tau. So those have the same, those define the same subspaces and the same reflections. So that's the 2 to 1 mapping of the quaternions to the rotation group. And think about it this way. The only difference between the 3D rotation group can be described entirely as reflections across 2 lines, pairs of lines, ordered pairs of lines, or across ordered pairs of planes that are orthogonal to those lines. That's SO3. That's rotation. Where quaternions come in is giving those lines or planes an orientation by picking a vector direction to describe them. That's really it. The space of pairs, ordered pairs of lines is isomorphic to SO3. The space of ordered pairs of unit vectors is the unit quaternions, and that's isomorphic to S3, the double cover. And that's essentially what's hidden in here. The simple algorithm is the fact that doing those reflections, reflecting across a line, just involves a dot product. So no transcendental functions. No transcendental functions, just summation and addition. And so the equivalence classes, the composition, this was, you can write ij equals k. This reveals that what is the quaternion associated with the 2 vectors? It's just their dot product and their cross product. Given 2 unit vectors, you have their dot product and cross product. That's 4 components, sum of squares is 1. That's a unit quaternion. How do you compose them if I know this dot product and that dot product and this dot product and that dot product? Quaternion multiplication is figuring out the cross pair if you put the middle ones together, just like vector addition. Given dot and cross, what's the new dot and cross? It's invariant, so it has to be that. And so that leads to a thing that quaternion I is not the same rotation as complex I. Complex I, we all know, is a quarter turn in the xy plane. Quaternion I, whether you do it by quaternion conjugation or by this method, is reflection across 2 vectors whose dot product is 0 and whose cross product is 1, 0, 0. That's the quaternion I. 0, 1, 0, 0. Dot product 0, they're orthogonal. cross product 1, 0, 0, that means they're J and K. And so this is a 180-degree rotation in the YZ plane. Very different than the complex I as a rotation. And so it gives you a very concrete way of thinking about quaternions. It makes these, what rotation they correspond to, very obvious. Because you think of a quaternion as a pair of unit vectors that express the scalar and vector part as their dot and cross product. That's, I think, still my favorite thing. Is you can view quaternions as pairs of vectors that express the scalar and vector part as their dot and cross product, and then the composition of those classes is, that would be geometric too, like vector addition, is quaternion multiplication, and that was beautifully presented in a recent book by next speaker on spherical geometry. Is that quaternion multiplication is, if you look at the ends of the unit vectors on the unit sphere, you get a beautiful spherical triangle and vector addition, which is basically, what's that? The great circle route. If you know the great circle route from New York to Paris, and the great circle route from Paris to London, then quaternion multiplication gives you the great circle route from New York to London. That's literally it. Beautiful. And here, there. You can also do interpolation in this way by making the first vector the same, unit vector the same, and you interpolate the second ones. And if it's not a unit, you just scale. So this does generalize to the full quaternions, and that's it. And I will give people, anyone who wants, we have 6 minutes or something. So if anyone wants 3D glasses, won't turn out the light. Where's my iPad? This, I can move this over into that screen.
Okay. I love this.
Oops. Bit PowerPoint. Now we have one. I want to show my phone. See this? Anyone want to? Yes. 3D glasses, lights out.
Lights out, yeah, wow.
Just let me see if I can actually. There. Yeah, lights out. This is kind of fun. Oh, there's my mouse. And so here, is there a way to get lights out? I don't know. Anyway, see here, I'm actually, anyone who wants to try it, I'm not, nothing up my sleeve. You can do this with your, I'm just pulling this one around with the mouse.
Yeah.
And there's the conic sections.
Nice.
There's
The toys.
yeah. There's torus knots. It's fun. You can change the numbers. And
This is so cool.
where was my favorite still is this. Oh, I think I have another version. There's the tangle trip. It should work with any. This one isn't 3D, but you can.
Yeah.
It should work with any number of even number of twists.
It's really beautiful.
So this is 8 twists, 4 times 2 turns, and there is doing the tangle twist, tangle trick of showing the simple connectedness of 2SO3, and using the point clouds also is fun. So I have to put that one into stereo. But all of this rotation is done by, as I move my mouse, each time I move my mouse, what's happening? My mouse is giving me a unit vector. Do we have a lights on? Much better with the lights out. Keep your 3D. Ooh, there.
Oh, somebody found it.
Yay. Okay. I think those look better because if you can get close enough so that you see the red and the green, then you do get a parallax effect and things will really look 3D because you get two different images because they're in your computer graphics, you have two cameras. So you have two camera viewpoints and that gives you the parallax. So, for instance, also all of these should have the torus knots as often the...
Oh, yeah, that's right.
Yeah, this one, yeah.
That's good.
There's torus knots. So this wraps a few times around the circle, so hopefully that one gives you a pretty
Oh,
good
yeah, that's-
separation
yeah,
of 3D.
Yep. that's-
So again, you can do your own 3D graphics pretty simply just by doing two images, and this is cheap. That you Pixar and Grant do much better things with better tools and make them available to us, which is really spectacular, but and helpful. And I want to learn how to do that more. But you can actually do it yourself. So there's torus knots without the torus. And kids really love these kind of things.
Like adults can.
Yeah, right.
Yeah.
And adults should too. Thank you. All right, thanks. Next speaker. Hopefully we can keep the legs open.
Thank